Functional language features, iterators, and closures. Rust design has taken inspiration from many existing languages and techniques, and one significant influence is functional programming. Programming in a functional style often includes using functions as values by passing them in arguments, returning them from other functions, assigning them to variables for later execution, and so forth. In this chapter, we don't debate the issue of what functional programming is or isn't, but we'll instead discuss some features of Rust that are similar to features in many languages often referred to as functional. More specifically, we'll cover closures, a function-like construct you can store in a variable, iterators, a way of processing a series of elements, how to use these two features to improve the input-output project in Chapter 12, the performance of these two features. Spoiler alert, they're faster than you might think. Other Rust features, such as pattern matching and enumerations, which will which we've covered in other chapters, are influenced by the functional style as well. Mastering closures and iterators is an important part of writing idiomatic, fast Rust code, so we'll devote this entire chapter to them. Closures, anonymous functions that can capture their environment. Rust closures are anonymous functions you can save in a variable or pass as arguments to other functions. You can create the closure in one place and then call the closure to evaluate it in another. No, evaluate in a different context. Unlike functions, closures can capture values from the scope in which they're defined. We'll demonstrate how these closure features allow for code reuse and behavior customization. Creating an abstraction of behavior with closures. Let's work on an example of a situation in which it's useful to store a closure to be executed later. Along the way, we'll talk about the syntax of closures, type, inference, and traits. Consider this hypothetical situation. We work at a startup that's making an app to generate custom exercise workout plans. The back end is written in Rust, and the algorithm that generates the workout plan takes into account many factors, such as the app user's age, body mass index, exercise preferences, recent workouts, and an intensity number they specify. The actual algorithm the actual algorithm used isn't important in this example. What's important is that this calculation takes a few seconds. We want to call this algorithm only when we need to, and only call it once so we don't need to make the user wait more than necessary. We'll simulate calling this hypothetical algorithm with the function simulated underscore expensive underscore calculation, showing in 13-1, which will print calculating slowly. Wait for 2 seconds and then return whatever number we passed in. Listing 13-1, a function to stand in for a hypothetical calculation that takes about 2 seconds to run. Next is the main function, which contains the parts of the workout app important for this example. This function represents the code that the app will call when a user asks for a workout plan. Because the interaction with the app's front end isn't relevant to the use of closures, we'll hard-code values representing inputs to our program and print the outputs. The required inputs are these: an intensity number from the user, which is specified when they request a workout to indicate whether they want a low intensity workout or a high intensity workout. A random number that will generate some variety in the workout plans. The output will be the recommended workout plan. Listing 13-2 shows the main function we'll use. Listing 13-2, a main function with hard-coded values to simulate users' input and random number generation. We've hard-coded the variable simulated underscore user underscore simplified specified underscore value as 10 and the variable simulated underscore random underscore number as 7. For simplicity's sake, in an actual program, we'd get the intensity number from the app front end, and we'd use the random crate to generate a random number, as we did in the guessing game example in Chapter 2. The main function calls a generate underscore workout function with the simulated input values. Now that we have the context, let's get to the algorithm. The function generate underscore workout in listing 13-3 contains the business logic of the app that we're most concerned with in this example. The rest of the code changes in this example. The rest of the code changes in this example will be made to this function. Listing 13-3, the business logic that prints the workout plans based on the input and calls to the simulated underscore expensive underscore calculation function. The code in listing 13-3 has multiple calls to the slow calculation function. The first if block calls simulated underscore expensive underscore calculation twice. The if inside the outer else doesn't call it at all. And the code inside the second else case calls it once. The desired behavior for the generate underscore workout function is to first check whether the user wants a low intensity workout, indicated by a number less than 25, or a high intensity workout, a number of 25 or greater. Low intensity workout plans will recommend a number of push-ups and sit-ups based on the complex algorithm we're simulating. If the user wants a high intensity workout, there's some additional logic. If the value of the random number generated by the app happens to be 3, the app will recommend a break and hydration. If not, the user will get a number of minutes of running based on the complex algorithm. This code works the way the business wants it to now. But let's say the data science team decides that we need to make some changes to the way we call the simulated underscore expensive underscore calculation code so that it calls the simulated underscore expensive underscore calculation function only once. We also want to cut the place where we're currently unnecessarily calling the function twice without adding any other calls to that function in the process. That is, we don't want to call it if the result isn't needed, and we still want to call it only once. Refactoring using functions. We could restructure the workout program in many ways. First, we'll try extracting the duplicated call to the simulated underscore expensive underscore calculation function into a variable as shown in listing 13-4. Listing 13-4 extracting the call to simulated underscore expensive underscore calculation to one place and storing the result in expensive underscore result variable. This change unifies all the calls to simulated underscore expensive underscore calculation and solves the problem of the first if block unnecessarily calling the function twice. Unfortunately, we're now calling this function and waiting for the result in all cases, which includes the inner if block that doesn't use the result value at all. We want to define code in one place in our program, but only execute that code where we actually need the result. And let's see, this is a use case for closure. Refactoring with closures to store code. Instead of always calling the simulated underscore expensive underscore calculation function before the if blocks, we can define a closure and store the closure in a variable rather than storing the result of the function call, as shown in listing 13-5. We can actually move the whole body of the simulated underscore expensive underscore calculation within the closure we're introducing here. Listing 13-5, defining a closure and storing it in the expensive underscore closure variable. The closure definition comes after the equals to assign it to the variable expensive underscore closure. To define a closure, we start with a pair of vertical pipes, inside which we specify the parameters to the closure. This syntax was chosen because of its similarity to closure definitions in Smalltalk and Ruby. The closure has one parameter named num. If we had more than one parameter, we would separate them with commas like param1, param2. After the parameters, we place curly brackets that hold the body of the closure. These are optional if the closure body is a single expression. The end of the closure after the curly brackets needs a semicolon to complete the let statement. The value returned from the last line in the closure body, num, will be the value returned from the closure when it's called. Because that line doesn't end in a semicolon, just as in function bodies. Note that this let statement means expensive underscore closure contains the definition of an anonymous function, not the resulting value of calling the anonymous function. Recall that we're using a closure because we want to define the code to call at one point. Store that code and call it at a later point. The code we want to call is now stored in expensive underscore closure. With the closure defined, we can change the code in the if block to call the closure to execute the code and get the resulting value. We call a closure like we do a function. We specify the variable name that holds the closure definition and follow it with parentheses containing the argument values we want to use as shown in listing 13-6. Listing 13-6 calling the expensive underscore closure we've defined. Now the expensive calculation is called in only one place, and we're only executing the code where we need the results. However, we've reintroduced one of the problems in listing 13-3. We're still calling the closure twice in the first if block, which will call the expensive code twice and make the user wait twice as long as they need to. We could fix this problem by creating a variable local to that if block to hold the result of calling the closure, but closures provide us with another solution. We'll talk about that solution in a bit, but first let's talk about why there aren't type annotations in the closure definition and the traits involved with closures. Closure type, interference, and annotation. Closures don't require you to annotate the type of parameters or their return values like functions do. The annotations are required on functions because they're part of an explicit interface exposed to the users. Defining this interface rigidly is important for ensuring that everyone agrees on what types of values a function uses and returns. But closures aren't used in an exposed interface like this. They're stored in variables and used without naming them and exposing them to users of the library. Closures are usually short and relevant only within the narrow context rather than in any arbitrary scenario. Within these limited contexts, the compiler is reliably able to infer the types of the parameters and the return type, similar to how it's able to infer the types of most variables. Making programmers annotate the types in these small anonymous functions would be annoying and largely redundant with the information the compiler already has available. As with variables, we can add type annotations if we want to increase explicitness and clarity at the code of being more verbose than is strictly necessary. Annotating the types for the closure we defined in listing 13-5 would look like the definition shown in listing 13-7. Listing 13-7, adding optional type annotations of the parameter and return value types in the closure. With type annotations added, the syntax of the closures looks more similar to the syntax of functions. The following is a vertical comparison of the syntax for the definition of a function that adds 1 to its parameter and a closure that has the same behavior. We've added some space to line up the relevant parts. This illustrates how closure syntax is similar to function syntax except for the use of pipes and the amount of syntax that is optional. The first line shows a function definition in the source line. Let's see, and the source. And the first line shows a function definition, and the second line shows a fully annotated closure definition. The third line removes the type annotations from the closure definition, and the fourth line removes the brackets, which are optional because the closure body has only one expression. These are all valid definitions that will produce the same behavior when they're called. Closure definitions will have one concrete type inferred for each of their parameters and for their return value. For instance, listing 13-8 shows the definition of a short closure that just returns the value it receives as a parameter. This closure isn't very useful except for the purpose of this example. Note that we haven't added any type annotations to the definition. If we then try to call the closure twice using the string as an argument the first time and a U32 the second time, we'll get an error. Listing 13-8 attempting to call a closure whose types are inferred with two different types. The compiler gives us this error. The first time we call example_closure with the string value, the compiler infers the type of X and the return type of the closure to be string. Those types are then locked into the closure in example_closure. And we get a type error if we try to use a different type with the same closure. Storing closures using generic parameters and the function traits. Let's return to our workout generation app. In listing 13-6, our code was still calling the expensive calculation closure more times than it needed to. One option to solve this issue is to save the result of the expensive closure in a variable for reuse and use the variable in each place we need the result, instead of calling the closure again. However, this method could result in a lot of repeated code. Fortunately, another solution is available. We can create a struct that will hold the closure and the resulting value of calling the closure. The struct will execute the closure only if we need the resulting value, and it will cache the resulting value so that the rest of our code doesn't have to be responsible for saving and reusing the result. You may know this pattern as memorization or lazy evaluation. To make a struct that holds a closure, we need to specify the type of the closure. Because a struct definition needs to know the types of each of its fields, each closure instance has its own unique anonymous type. That is, even if two closures have the same signature, their types are still considered different. To define structs, enumerations, or function parameters that use closures, we use generics and trait bounds, as we discussed in Chapter 10. The function traits are provided by the standard library. All closures implement at least one of the traits: function, function mute, or function once. We'll discuss the difference between these traits in Capturing the Environment with Closures section. In this example, we can use the function trait. We add types to the function trait bound to represent the types of the parameters and return values the closures must have to match this trait bound. In this case, our closure has a parameter of type U32 and returns a U32. So the trait bound we specify is function U32, U32. Listing 13-9 shows the definition of the catcher struct that holds a closure and an optional result value. Listing 13-9 defining a catcher struct that holds a closure in calculation and an optional resultant value. The catcher struct has a calculation field of the generic type T. The trait bounds on T specify that it's a closure by using the function trait. Any closure we want to store in the calculation field must have one U32 perimeter specified within the parentheses after function. This must return a U32 specified after the arrow, which is, I'm guessing, just a dash, which is going to be either considered an N dash, a hyphen, or a minus with a greater than sign. Note, functions can implement all three of the function traits too. If we want to do doesn't, let's see, if what we want to do doesn't require capturing a value from the environment. We can use function rather than a closure where we need something that implements an function trait. The value field is of type option less than U32 greater than. Before we execute the closure, value will be none. When code using a catcher asks for the result of the closure, the catcher will execute the closure at that time and store the result within some variant in the value field. Then, if the code asks for the result of the closure again, instead of executing the closure again, the catcher will return the result held in the sum variant. The logic around the value field we've just described is defined in listing 13-10. Listing 13-10, the catching logic of catcher. We want catcher to manage the struct field values rather than letting the calling code potentially change the values in these fields directly, so these fields are private. The catcher, and those are going to be, forgive me for the time here. Yeah, I don't have that listed in front of me. Colon, okay. I'm getting those confused with other things, but I'll try to do better in the future videos. The catcher new function takes a generic parameter t, which we've defined as having the same trait bound as the catcher struct. The catcher new returns a catcher instance that holds the closure specified in the calculation field and a none value in the value field because we haven't executed the closure yet. When the calling code needs the result of evaluating the closure, instead of calling the closure directly, it will call the value method. This method checks whether we already have a resulting value in self.value in some If we do, it returns the value within the sum without executing the closure again. The self dot value is none. The code calls the closure stored in self dot calculation, saves the result in self dot value for future use, and returns the value as well. Listing 13-11 shows how we can use the catcher struct in function generate underscore workout from the listing in 13-6. Listing 13-11 in, using catcher in the generate underscore workout function to abstract a way of catching logic. Instead of saving the closure in a variable directly, we save a new instance of catcher that holds the closure. Then, in each place we want the result, we call the value method on the catcher instance. We can call the value method as many times as we want or not call it at all, and the expensive calculation will be run a maximum of once. Try running this program with the main function from listing 13-2. Change the values in simulated underscore user underscore specified underscore value and simulated underscore random underscore number variables to verify that in all the cases in the various if and else blocks, calculating slowly appears only once and only when needed. The catcher takes care of the logic necessary to ensure we aren't calling the expensive calculation more than we need so. Generate underscore workout can focus on the business logic. Limitations of the catcher implementation. Catching values is generally useful behavior that we might want to use in other parts of our code with different closures. However, there are two problems with the current implementation of catcher that would make reusing it in different contexts difficult. The first problem is that a catcher instance assumes that we will always get the same value for the parameter argument to the value method. That is, this test of catcher will fail. This test creates a new catcher instance with a closure that returns the value passed into it. We call the value method on this catcher instance with an argument value of 1 and then an argument value of 2. And then we expect the call to value with the argument value of 2 to return 2. Run this test with the catcher implementation in listing 13-9 and listing 13-10, and the test will fail on the assert underscore EQ exclamation mark with the message. The problem is that the first time we called C period value with 1, the catcher instance saved some, and that is going to be parentheses, saved some parenthesis 1 parenthesis self dot value. Therefore, no matter what we pass into the value method, it will always return 1. Try modifying catcher to hold a hash map rather than a single value. The keys of the hash map will be the argument values that are passed in, and the values of the hash map will be the result of calling the closure on that key. Instead of looking at whether self.value directly has some or a none value, the value function will look up the argument in the hash map and return the value if it is present. If it's not present, the catcher will call the closure and save the resulting value in the hash map associated with the argument value, with its argument value. The second problem with the current catcher implementation is that it only accepts closures that take one parameter of type U32 and return a U32. We might want to cache the results of closures that take a string slice and return U-size values, for example. To fix this issue, try introducing more generic parameters to increase the flexibility of the catcher functionality. Capturing the environment with closures. In the workout generator example, we only use closures as inline anonymous functions. However, closures have an additional capability that functions do not have. They can capture their environment and access variables from the scope in which they are defined. Listing 13-12 has an example of a closure stored in the equal underscore to underscore x variable that uses the x variable from the closure surrounding environment. Listing 13-12, example of a closure that refers to a variable in its enclosing scope. Here, even though x is not one of the parameters of equal underscore to underscore x, the equal underscore to underscore x closure is allowed to use the x variable that's defined in the same scope that equal underscore to underscore x is defined in. We can't do the same with functions. If we try the following example, our code won't compile. We'll get an error. The compiler even reminds us that this only works with closures. When a closure captures a value from its environment, it uses memory to store the values for use in the closure body. This use of memory is overhead that we don't want to pay in more common cases, where we want to execute code that doesn't capture its environment. Because functions are never allowed to capture their environment, defining and using functions will never incur this overhead. Closures can capture values from their environment in three ways, which directly map to the three ways a function can take a parameter: taking ownership, borrowing mutability, and borrowing mutability and borrowing immutability. These are encoded in the three function traits as follows. Function once consumes the variables it captures from its encoding scope, known as the closure's environment. To consume the captured value, the closure must take ownership of these variables and move them into the closure when it is defined. The once part of the name represents the fact that the closure can't take ownership of the same variable more than once, so it can only be called it can only be called only once. Function mute can change the environment because it mutably borrows values. Function borrows values from the environment immutability. When you create a closure, Rust infers which trait to use based on how the closure uses the value from the environment. All closures implement function once because they can all be called at least once. Closures that don't move the captured variables also implement function mute, and closures that don't need mutable access to the captured variables also implement function. In listing 13-12, the equal underscore to underscore x closure borrows x immutability. So equal underscore to underscore x has the function trait because the body of the closure only needs to read the value in x. If you want to force the closure to take ownership of the values, it uses the environment. So you can use the move keyword before the perimeter list. This technique is mostly useful when passing a closure to a new thread to move the data so it's owned by the new thread. We'll have more examples of move closures in Chapter 16 when we'll talk about concurrency. For now, here's the code from listing 13-12 with the move keyword added to the closure definition and using vectors instead of integers because integers can be copied rather than moved. Note that this code will not yet compile. We'll receive the following error. The x value is moved into the closure when the closure is defined. Because we added the move keyword, the closure then has ownership of x, and main isn't allowed to use x anymore in the print line exclamation mark statement. Removing print line exclamation mark will fix this example. Most of the time, when specifying one of the function trait bounds, you can start with function and the compiler will tell you if you need function mute or function once based on what happens in the closure body. To illustrate situations where closure can capture their environment are useful as function perimeters, let's move on to our next topic, iterators. Processing a series of items with iterators. The iterator pattern allows you to perform some task on a sequence of items in turn. An iterator is responsible for the logic of iterating over each item and determining when the sequence has finished. When you use iterators, you don't have to re-implement the logic yourself. In Rust, iterators are lazy, meaning they have no effect until you call methods that consume the iterator to use it up. For example, the code in listing 13-13 creates an iterator over the items in the vector v1 by calling the iter method defined on vector t. The code by itself doesn't do anything useful. Listing 13-13 creating an iterator. Once we've created an iterator, we can use it in a variety of ways. In listing 3-5 in chapter 3, we used iterators with for loops to execute some code on each item. Although we glossed over what the call to iter did until now. The example in listing 13-14 separates the creation of an iterator from the use of the iterator in the for loop. The iterator is stored in the v1 underscore iter variable, and no iteration takes place at that time. When the for loop is called using the iterator in v1 underscore iter, each element in the iterator is used in one iteration of the loop, which prints out each value. Listing 13-14 use an iterator in a for loop. In languages that don't have iterators provided by their standard libraries, you would likely write this same functionality by starting a variable at index 0, using that variable to index into the vector to get a value, and incrementing the variable value, in a loop until it reached the total number of items in the vector. Iterators handle all that logic for you, cutting down on repetitive code you could potentially mess up. Iterators give you more flexibility to use the same logic with many different kinds of sequences, not just data structures you can index into like vectors. Let's examine how iterators do that. The iterator trait and the next method. All iterators implement a trait named iterator that is defined in the standard library. The definition of the trait looks like this. Notice this definition uses some new syntax: type item and self : item. Verify that that's colon, and it is, which are defining an associated type with this trait. We'll talk about associated traits in depth in Chapter 19. For now, all you need to know is that this code says implementing the integrator trait requires that you also define an item type, and this item type is used in the return type of the next method. In other words, the item type will be the type returned from the iterator. The iterator trait only requires implementers to define one method. The next method, which returns one item of the iterator at a time wrapped in sum, and when iteration is over, returns none. We can call the next method on iterators directly. Listing 13-15 demonstrates what values are returned from repeated calls to next on iterator created from the vector. Listing 13-15, calling the next method on an iterator. Note that we needed to make v1 underscore iter mutable. Calling the next method on an integrator changes internal state that the iterator uses to keep track of where it is in the sequence. In other words, this code consumes or uses up the iterator. Each call to next eats up an item from the iterator. We didn't need to make v1 underscore iter mutable when we used it for loop because the loop took ownership of v1 underscore iter and made it mutable behind the scenes. Also note that the value we get from the calls to next are immutable reference to the values in the vector. The iter method produces an iterator over immutable references. If we want to create an iterator that takes ownership of v1 and returns owned values, we can call into underscore iter instead of iter. Similarly, if we want to iterate over mutable references, we can call iter underscore mute instead of iter. Methods that consume the iterator. The iterator trait has a number of different methods with default implementations provided by the standard library. You can find out about these methods by looking in the standard library API documentation for the iterator trait. Some of these methods call the next method in their definition, which is why you're required to implement the next method when implementing the iterator trait. Methods that call next are called consuming adapters because calling them uses up the iterator. One example is the sum method, which takes ownership of the iterator and iterates through the items by repeatedly calling next, thus consuming the iterator. As it iterates through, it adds each item to a running total and returns a total when iteration is complete. Listing 13-16 has a test illustrating a use of the sum method. Listing 13-16 calling the sum method to get the total of items in the iterator. We aren't allowed to use v1 underscore iter after the call to sum because sum takes ownership of the iterator we call it on. Methods that produce other iterators. Other methods defined on the iterator trait known as iterator adapters allow you to change iterators into different kinds of iterators. You can chain multiple calls to iterator adapters to perform complex actions in a readable way, but because all iterators are lazy, you have to call one of the consuming adapter methods to get results from calls to iterator adapters. Listing 13-17 shows an example of calling the iterator adapter method, map, which takes a closure to call on each item to produce a new iterator. The closure here creates a new iterator in which each item from the vector has been incremented by 1. However, this code produces a warning. Listing 13-17 calling the iterator adapter map to create a new iterator. The warning we get is this. The code in listing 13-17 doesn't do anything. The closure we've specified never gets called. The warning reminds us iterator adapters are lazy and we need to consume the iterator here. To fix this and to consume the iterator, we'll use the collect method which we used in chapter 12 with envelope : arguments in listing 12-1. This method consumes the iterator and collects the resulting values into a collection data type. In listing 13-18, we collect the results of iterating over the iterator that's returned from the call to map into a vector. This vector will end up containing each item from the original vector incremented by 1. Listing 13-18 calling the map method to create a new iterator and then calling the collect method to consume the new iterator and create a vector. Because map takes a closure, we can specify any operation we want to perform on each item. This is a great example of how closures let you customize some behavior while reusing the iteration behavior that the iterator trait provides. Using closures that capture their environment. Now that we've introduced iterators, we can demonstrate a common use of closures that capture their environment by using the filter iterator adapter. The filter method on an iterator takes a closure that takes each item from the iterator and returns a boolean. If the closure returns true, that value will be included in the iterator produced by filter. If the iterator returns false, the value won't be included in the resulting iterator. In listing 13-19, we use filter with a closure that captures the shoe underscore size variable from its environment to iterate over a collection of shoe struct instances. It will return only shoes that are the specified size. Listing 13-19 using the filter method with a closure that captures shoe underscore size. The shoes underscore in underscore my underscore size function takes ownership of a vector of shoes and a shoe size as parameters. It returns a vector containing only shoes of the specified size. In the body of shoes underscore in underscore my underscore size, we call into underscore iter to create an iter to take ownership of the vector. Then we call filter to adapt the iterator into a new iterator that only contains elements for which the closure returns true. The closure the closure captures the shoe underscore size parameter of the environment and compares the value with each shoe size, keeping only shoes of the size specified. Finally, calling the collect gathers the values returned by the adapted iterator into a vector that's returned by the function. The test shows that when we call shoes underscore in underscore my underscore size, we get back only shoes that have the same size as the value we specified. Creating our own iterator with the iterator trait. We've shown that you can create an iterator by calling iter into underscore iter or iter underscore mute on a vector. You can create iterators from the other collection types in the standard library, such as HashMap. You can also create iterators that do anything you want by implementing the iterator trait on your own types. As previously mentioned, the only method you're required to provide a definition for is the next method. Once you've done that, you can use all the methods that have default implementations provided by the iterator trait. To demonstrate, let's create an iterator that will only ever count from 1 to 5. First, we'll create a struct to hold some values. Then we'll make this struct into an integrator by implementing the iterator trait by using the values in that implementation. Listing 13-20 has the definition of the counter struct and an associated new function to create instances of counter, : Listing 13-20 defining the counter struct and a new function that creates instances of counter with an initial value of 0 for count. The counter struct has one field name, count. This field holds a U32 value that will keep track of where we are in the process of iterating from 1 to 5. The count field is private because we want the implementation of counter to manage its value. The new function enforces the behavior of always starting the new instance with a value of 0 in the count field. Next, we'll implement the iterator trait for our counter type by defining the body of the next method to specify what we want to happen when the iterator is used, as shown in listing 13-21. Listing 13-21 implementing the iterator trait on our counter struct. We set the associated item type for our iterator to U32, meaning the iterator will return U32 values. Again, don't worry about associated types yet. We'll cover them in Chapter 19. We want our iterator to add 1 to the current state, so we initialized count 0 to 0 so it would return 1 first. If the value of count is less than 6, Next, we'll return the current value wrapped in sum. But if count is 6 or higher, our iterator will return none. Using our counter iterators next method. Once we've implemented the iterator trait, we have our iterator. Listing 13-22 shows a test document demonstrating that we can use the iterator functionality of our counter struct by calling the next method on it directly, as we did with the iterator created from a vector in listing 13-15. Listing 13-22, testing the functionality of the next method implementation. This test creates a new counter instance of the counter variable and then calls next repeatedly, verifying that we have implemented the behavior we want this iterator to have, returning the values from 1 to 5. Using other iterator trait methods. We implemented the iterator trait by defining the next method. So we can now use any iterator trait method default implementations as defined in the standard library because they all use the next method's functionality. For example, if for some reason we wanted to take the values produced by an instance of counter pair with the values produced by another counter instance after skipping the first value, multiply each pair together, keep only those results that are divisible by 3, and add all the resulting values together, we could do so as shown in the test in listing 13-23. Listing 13-23 using a variety of iterator trait methods on our counter iterator. Note that zip produces only 4 pairs. The theoretical fifth pair, 5, none, is never produced because zip returns none when either of its input iterators return none. All of these method calls are possible because we specified how the next method works, and the standard library provides default implementations for each method that call next. Improving our in-out project. With this new knowledge about iterators, we can improve our in-out project in Chapter 12 by using iterators to make places in the code clearer and more concise. Let's look at how iterators can improve our implementation of the config : new function and the search function. Removing a clone using an iterator. In listing 12-6, we used code that took a slice of string values and created an instance of config struct by indexing into the slice and cloning the values, allowing the config struct to own those values. In listing 13-24, we've reproduced the implementation of the config : new function as it was in listing 12-23. Listing 13-24, reproduction of the config : new function from listing 12-23. At the time, we said not to worry about the inefficient clone calls because we would remove them in the future. Well, that time is now. We needed clone here because we have a slice with string elements in the perimeter arguments, but the new function doesn't own arguments. To return ownership of the config instance, we had to clone the values of the query and the file name fields of config so so the config instance can own its values. With our new knowledge about iterators, we can change the new function to take ownership of an iterator as its arguments instead of borrowing a slice. We'll use iterator functionality instead of the code that checks the length of the slice and indexes it into specific locations. This will clarify what the config : new function is doing because the iterator will access the values. Once config : new takes ownership of the iterator and stops using the indexing operations that borrow, we can move the string values from the iterator into config rather than calling clone and making a new allocation. Using the return iterator directly. Open your in-out project source/main.rs file, which should look like this. We'll change the start of the main function that we had in listing 12-24 to the code in listing 13-25. This won't compile until we update config : new as well. Listing 13-25 passing the return value of envelope : arguments to config : new. The envelope : arguments function returns an iterator rather than collecting the integer values into a vector and then passing a slice to config : new. Now we're passing ownership of the iterator return from the envelope : arguments to config : new directly. Next, we need to update the definition of config : new in our in-out project source/libraries.rs file. Let's change the signature of config : new to look like listing 13-26. This still won't compile because we need to update the function body. Listing 13-26, updating the signature of config : new to expectant integer. The standard library documentation for envelope : arguments function shows that the type of iterator it returns is standard library : envelope : arguments. We've updated the signature of the config : new function so that the perimeter arguments has the type standard library : envelope : arguments instead of the reference close bracket strings close brackets because we're taking ownership of arguments. Are those close brackets? Yes, they are. Okay, because we're taking ownership of arguments and we'll be muting arguments by iterating over it. We can add the mute keyword into the specification of the argument's perimeter to make it mutable, using iterator trait methods instead of indexing. Next, we'll fix the body of config : new. The standard library documentation also mentions that standard library : envelope : arguments implements the iterator trait, so we know we can call the next method on it. Listing 13-27 updates the code from listing 12-23 to use the next method. Listing 13-27 changing the body of config : new to use iterator methods. Remember that the first value in the return value of envelope : arguments is the name of the program. We want to ignore that and get to the next value. So first we'll call next and do nothing with the return value. Second, we call next to get the value we want to put in the query field of config. If next returns a sum, we use a match to extract the value. If it returns none, it means not enough arguments were given and we return early with error value. We do the same thing for file name value. Making code clearer with Iterator adapters. We can also take advantage of iterators in the search function of our IO project, in-out project, which is reproduced here in listing 13-28 as it was in listing 12-19. Listing 13-28, the implementation of search function from listing 12-19. We can write this code in a more concise way using iterator adapter methods. Doing so lets us avoid having a mutable intermediate results vector. The functional programming style prefers to minimize the amount of mutable state to make code cleaner. Removing the mutable state might enable a future enhancement to make searching happen in parallel because we wouldn't have to manage concurrent access to the results vector. Listing 13-29 shows this change. Listing 13-29 using iterator adapter methods in implementation of the search function. Recall that the purpose of the search function is to return all lines in contents that contain the query. Similar to the filter example in listing 13-19, this code uses the filter adapter to keep only the lines that line dot contains query returns true for. We then collect the matching lines into another vector with collect. Much simpler. Feel free to make the same change to use iterator methods in the search underscore case underscore insensitive function as well. The next logical question is which style you should choose in your code and why. The original implementation in listing 13-28 or the version using iterator in the listing 13-29. Most Rust programmers prefer to use the iterator style. It's a bit tougher to get the hang of at first, but once you got a feel for the various iterator adapters and what they do, iterators can be easy to understand. Instead of fiddling with the various bits of looping and building new vectors, the code focuses on the high-level objective of the loop. This abstracts away some of the commonplace code so it's easier to see the concepts that are unique to this code, such as the filtering condition each element in the iterator must pass. But are the two implementations truly equivalent? The intuitive assumption might be that the more low-level loop will be faster. Let's talk about performance. Comparing performance loops versus iterators. To determine whether to use loops or iterators, you need to know which versions of our search functions faster. The version with an explicit for loop or the version with iterators. We ran a benchmark by loading the entire contents of the Adventures of Sherlock Holmes by Sir Arthur Conan Doyle into a string and looking for the word the in the contents. Here are the results of the benchmark on the version of search using the for loop and the version using iterators. The iterator version was slightly faster. We don't explain the benchmark code here because the point is not to prove that the two versions are equivalent, but to get a general sense of how these two implementations compare performance-wise. For a more comprehensive benchmark, you should check using various texts of various sizes as the contents, different words and words of different lengths as the query, and all kinds of other variations. The point is, iterators, although a high-level abstraction, get compiled down to roughly the same code as if you'd written a lower level code yourself. Iterators are one of Rust's zero-cost abstractions, by which we mean using the abstraction imposes no additional runtime overhead. This is analogous, analogous to how Bjarne Stroustrup, the original designer and implementer of C++, defines zero overhead in Foundations of C++ 2012. In general, C++ implementations obey the zero overhead principle that you don't use what you don't use, you don't pay for. And further, what you do use, you couldn't hand code any better. As another example, the following code is taken from an audio decoder. The decoding algorithm uses a linear prediction mathematical operation to estimate further values based on a linear function of the previous samples. This code uses an iterator chain to do some math on three values in scope: a buffer slice of data, an array of 12 cacophonies, and the amount by which to shift data in QLP underscore shift. We've declared the variables within this example, but not given them any values. Although this code doesn't have much meaning outside of its context, it's still a concise, real-world example of how Rust translates high-level ideas to low-level code. To calculate the value of prediction, this code iterates through each of the 12 values in coefficients and uses the zip method to pair the coefficient value with the previous 12 values in buffer. Then, for each pair, we multiply the value together, sum all the results, and shift the bits in the sum QLP underscore shift bits to the right. Calculations in applications like audio decoders often prioritize performance most highly. Here we're creating an iterator using two adapters and then consuming the value. What assembly code would this Rust code compile to? Well, as of this writing, it compiles down to the same assembly you'd write by hand. There's no loop at all corresponding to the iteration over the values in coefficients. Rust knows that there are 12 iterations, so it unrolls the loop. Unrolling is an optimization that removes the overhead from the loop controlling code and instead generates repetitive code for each iteration of the loop. All of the coefficients get stored in registers, which means accessing the values is very fast. There are no bounds checks on the array access at runtime. All these optimizations that Rust is able to apply make the resulting code extremely efficient. Now that you know this, you can use iterators and closures without fear. They make the code seem like it's higher level, but don't impose a runtime performance penalty for doing so. Summary. Closures and iterators are Rust features inspired by functional programming language ideas. They contribute to Rust's capability to clearly express high-level ideas at low-level performance. The implementations of closures and iterators are such that runtime performance is not affected. This is part of Rust's goal to strive to provide a zero-cost abstractions. Now that we've improved, now that we've improved the expressiveness of our in-out.io project, let's look at some more features of Cargo that will help us share the project with the world. That concludes Chapter 13. Next up is Chapter 14.